Hey everyone, my name is Gavin Christopher Dowd, and today I'm here to talk about Physics 2212 Lab 1 charge tape. The goals of this lab is to show the movement of charge from two neutral pieces of tape. And the basic idea is that when you take these two neutral objects and you place them next to each other, so these two shapes, and you rub them down against each other, the charge is going to move or separate. And when you end up separating the two pieces of tapes, there's going to be a net charge on both pieces of tape. One will be positive and one will be negative. So for the experiment, we're just going to be taking two pieces of tape, or we're going to be placing them on a base tape and then creating a net charge on each tape, which I'll describe in more detail a little later. Besides that, we're going to then be taking those two charged tapes, which should have the same charge. We're going to place them at a distance in which one of the tapes will be floating due to the electric force, which can be seen below, with 1 over 4 pi epsilon times the two charges over the magnitude of the distance squared, which will be equal to the force of gravity. And we're going to be making some key assumptions. These assumptions are that the tapes are acting as point charges, which is because the charge should be evenly spread throughout the two pieces of tapes, which means that the center of mass can be seen as like the center of charge, so we can just treat it as a point charge. If the tapes will also have equal charges because they're going to be the same distance, and we're using the same base tape to create these net charges. We're also going to be assuming no air resistance just to make math a little easier. So the details behind the actual experiment, as I said earlier, we have our base tape and our U tape, in which we rip the two off one another, and the spread of charge is redistributed and the tape we care about, and for our experiment it had a net positive charge. This was tested by rubbing a mechanical pencil along my hair, which gives the pencil a negative charge, and which it was attracted to the piece of the tape, meaning the tape had to be positive. And now some details for the actual experiment itself. Both our pieces of tape were 8 inches, which when converting to meters, which is just multiplying 8 times 2.54 centimeters, and then dividing that by 100, you get 0.2052 meters. The measured distance between the two was 5 millimeters, or 5 times 10 to the negative 3 meters. And the mass of the tape was 20 times 10 to the negative 6. It's a very light piece of tape. So for the experiment itself, we're looking for a few things. We're looking for the deficit electrons. We're looking for the charge of our tape. We're looking for the total number of atoms. We're looking for the ratio. And so on the left here for my code is mainly just defining all my constants. And we're also defining the spheres for our charges, because we're assuming that tapes are just a point charge. And to actually calculate the charge, we just set our force of gravity equal to our electric force, because we know all the other units except for the charge, which since the charge is equal, we can just write as q squared, and you can solve for that fairly easily. And once that's done, you just plug these all into these equations seen on the right. The deficit electrons is just taking that charge you found and dividing it by the total number of electrons, because that should hypothetically tell you the total charge. It can also be the same with protons, because protons and electrons have the same charge. The total number of atoms is just taking the area of the tape, and we're just dividing it by the area of an atom, and then we're just taking the ratio of deficit electrons and dividing it by the total number of atoms. So the results of the lab, we found that the net force is basically 0. It's a very infinitesimally small number. I've seen it's like to the negative 20. There's a net charge of the tape of 7.4 times 10 to the negative 10. There's the total number of atoms on the tape was 20 times 10 to the 8th. The total deficit electrons was 46 times 10 to the 8th. And we found that there was like a ratio of 2.25 deficit electrons to total number of atoms. The only differences we found from the calculations was just the net force, which it's really not a big deal, just due to how small it was. Some possible areas where this might have come from were the three simplifying assumptions we make. Reality is not, doesn't work how our predictions said they would, so there's going to be some differences between the two. And the other thing is just human error. Like when we measured the distances between the tapes, we were eyeballing it with, and we were looking at it for millimeters, so it's not easy to get to fully accurate results from that. So the what if statement asks what happens if electrons had a positive charge, and the answer is nothing. Nothing will change. Whether or not electrons have a positive or negative charge is kind of irrelevant, because at the end of the day, like will always repel like and opposites will attract. So regardless if electron's positive or negative, that doesn't change anything about the experiment itself. The what does it mean question asks why don't we just like handle tape? Why do we have to be super careful about it? And that's just because charge is kind of really antisocial. It basically doesn't want to be around other same charges. So when you put a neutral object involved, the charges that a net charge will try to move on to that other surface, and that will make the object neutral. So thank you for watching.